Hello, we are Team Pong.
Meet the team. So my name is Richard Liao. I'm an electrical engineering, and I'm a sophomore.
My name is Rishi. I'm a sophomore in computer engineering.
My name's Arnav, and I'm a sophomore in computer engineering.
I'm Aarush. I'm a freshman in computer engineering.
And then our peer mentor for this project is Gensi Duraku.
So for our presentation overview, we want to first wrap into our design. So as our design begins, our whole goal is to create VGA Pong. So Pong was one of the first games ever created, and we're really interested in creating this game using system Verilog. So our goal was to do this in under 1,000 cell limit, and our goal was to simulate two paddles, one on the left, one on the right, and a ball that can move in the X and Y direction, while the paddles can only move in the Y direction. So moving to our main reason for doing this, why Pong in System Verilog? System Verilog is a hardware description language where as EC majors, it gave us a fresh start on hardware development, and creating a game seemed the most fun for us as we all grew up playing video games and all of that sort. So if we can go to the System Verilog description slide, it gives us small details of what we were doing. And our design is a two-player Pong game where two people can control a paddle, and it's all written in System Verilog, which once again, a hardware description language that basically models how hardware would interact with our code and how it works.
So project specifications. As an overview, so we're going to generate real-time video output for the game display, and the way we do that is through standard VGA interface. So VGA is just like kind of like your HDMI cord. VGA is like an alternative for that, but more lower level and basic. I think it was used in the first monitors, and then we'll be using the VGA interface at a 25 megahertz clock. And then the second thing is that we'll be capturing and processing the two-player control inputs. So that's like the up and down buttons for the paddles, start and reset for the game. And then finally, we'll be implementing game logic without like external memory or CPU. So the way we're doing that is we're going to be minimizing memory and utilizing as much combinational logic as possible. So this is the system level inputs and outputs. So first we have two pins for the clock and the reset, and this is important for the timing registers and resetting the game overall. And then we have the VGA sync signals. So VGA has horizontal and vertical sync signals, and this is important just to keep the VGA in track of like where it is along the monitor. So that's another two pins. And then as mentioned before, we have the player one and player two movement controls. So that's up and down for both players, plus the start button. So that's five pins. And then we'll also have a 1-bit like pixel output. So that's what's going to determine what pixels turn black and what pixels turn white. And so that would be three pins. And then this is our tape out plan. So if we haven't mentioned it before, we're going to be doing this in black and white, just like the original Pong game. So that way we only have a 0 for black and then a 1 for white. So that's for each pixel. And then we also have our input in physics. So we need to keep track of like the buttons that the players press, and then also calculating collision physics, like when the ball hits the top of the screen or when the ball hits a paddle. And then as we mentioned before, we're going to be generating the pixels in real time and minimizing as much logic as possible, combinational logic as possible. And then we have had a few limitations with our project since we'll be like taping out as a physical chip. And one of the limitations is that we need to be under 1,000 cells. So as reference, like memory is around 3 cells per register, and then combinational logic is about 1 per gate. So we're going to be trying to minimize memory and utilize as much combinational logic as possible to keep the area under 1,000 cells. And then also we're limited by a 66 megahertz clock. So that's why we're operating the VGA at 25 megahertz, which is well within limit. And then we'll also be only using 11 total pins. So moving on to the RTL design, this is the overall diagram that we have. As you can see, we have three main modules, one of them VGA, the next one pixel generation, and the third one game logic. And so you can see the overall flow of logic here, where we have all the input pins go straight into the game logic module. And then from there, the game logic module will update the X and Y coordinates for all for the ball and the paddles, which will be sent to the pixel generation module, which also receives inputs from the VGA monitor. And then finally, the pixel generation module will output each pixel's 0 or 1, so it's black or white.
So as Richard explained, this is our VGA RTL. So we have a clock divider as our enable signal going to a horizontal and vertical counter, which then goes into our logic for how the horizontal and vertical counter would go, which gives us an output of our current X and Y coordinates, whether it be the ball or the paddles, as well as a display on signal, which tells us is the display on, is everything working, and a horizontal sync and a vertical sync signal, which it will be sent to different game logic signals, as well as or the game logic module, and different modules to determine how the console would run.
So in terms of the game logic RTL, the way we are controlling the paddles and the ball logic is with a control for both player one and player two, which is 2 bits each. There's a 1 for going up and a 0 for going up and a 1 and 0 for going down for each player. So that gets fed into logic that changes the position of the paddles depending on how the combination of the controls, and then the Y values of each paddle are updated accordingly, and that's sent out to the pixel generation logic so that the paddle can be displayed on the screen. And then the Y paddle logic is also fed into the ball logic modules, which are 10 bits each for the pixel sizes on the screen, and those go into the ball logic where the velocity is X and Y of the ball, and the paddle logic is all combinational logic. And that goes into a separate module to update it takes in the current ball X and Y values and gives new ball and X and Y values. Those go to the pixel generation as well to be displayed. And then that new state is fed back into the current state so that this same calculations can be done for the next clock cycle.
Here's the roadmap of how we are taking this from a concept to actual tape-out. We will start with overall block diagrams. Once that's done, we move into RTL diagrams. Then we do system Verilog implementation. Once all of that is done, we do FPGA prototyping, where we simulate everything to catch bugs before they become permanent. Then we move on to synthesis and optimization, making sure that design works and is fast. We finally debug it, and if everything checks out, we hit the final tape-out milestone. And we do the final tape-out. We have broken this semester into 4 clear phases. Phase 1 is where we finalize the VGA module, RTL diagrams for game diagrams for game logic and pixel generation. Phase 2 is where we implement game logic and pixel generation. Phase 3 is where we verify design on FPGA and optimize logic to meet the cell count limits. Phase 4 is where we execute design, routing, and final tape execution.
So this is our division of labor. So starting off with me, I'll be handling the RTL implementation as well as the verification.
I'm working on the integration, making sure all the modules can work together, and the FPGA implementation.
And I created the game logic RTL with the paddle movement logic as well as the functional verification.
I'm working on timing analysis and peripherals.
And as far as Gantt chart goes, so far we have accomplished creating the system Verilog modules for the game logic, the pixel generation, and the VGA. And we're working on test benching for the VGA and the game logic, and our test benching for the pixel generation is already fully complete and verified. So as for the chart goes, currently we're working on the player controls with which Aarush is working on and plans to have done within the next 1 to 2 days. We're also working on the VGA test benching, which is hoped to be completed in the next 4 or 5 days. And once all of our test benching is done, that's when we move on to the verification and the actual implementation where we can test our final product onto a monitor with using an FPGA board. And once that's complete, our last portion is open lane configuration and tape out, which is the final portion we mentioned earlier, where we actually get our game fit to run on a chip and manufacture.
Our references for this project is once again going back to creating Pong as how it was made originally. 2 paddles, one on the left, one on the right. They both move up and down, and a ball that can move either side to side or up and down. And then our biggest reference was our peer mentor, Gensi. So for starters, he created a Street Fighter project, and he was the one who basically helped us bring our idea to life, whether helping us figure out our VGA timing, helping us figure out how to do an integration, how to do FPGA implementation, how to make most of our logic and most of our how we were able to design our project was based on our peer mentor giving us guiding direction and a good chunk of literature as well as work to go back on and review. Thank you so much for listening to our presentation.
Thank you.
Thank you.